Hey everyone, and welcome to the third video of the vectors topic. This one's going to be relatively content heavy. I'm going to be going over a couple of worked examples. It's going to deal with a lot of the vector algebra and extending some of the vector algebra into real-world applications, as the title suggests of this video. And these generally are the most time-consuming questions in tests and exams. So this is a relatively important video, and it only gets more complex with the addition of a third dimension in year 12. So in terms of the unit outline, we're going to be looking at properties of parallel and perpendicular vectors, determining if two vectors are parallel and or perpendicular using scalar product rules or scalar multiples, and I'll go over how that kind of works. We'll also be having a look at projections of vectors, as well as solving problems involving displacement, force, and velocity involving the above concepts. One of the key points we have here is collision/interception as a key example of a real-world application of vector arithmetic and vector algebra that we can use, and closest approach as well is very common as well. Another thing is being able to adjust a plane's velocity according to considering the fact that there might be some adjustment because of wind, or having a boat go from a point A to a point B, having to adjust for a flow of current. And we'll have a look at all of those examples over the course of this video. I'll see if I can pull some test questions together and we'll go over those. So let's get straight into the video then. Okay, so the first thing I'm going to do is I'm going to examine some of the properties of parallel and perpendicular vectors. And I'll see here that the scalar product is really important, particularly for perpendicular vectors, and it has a range of applications later on down the track. So in terms of parallel vectors are vectors that are in the same direction. They can, in the same sort of direction or the opposite direction. So you can have parallel vectors that head in opposite directions, and they can have differences in magnitude. Parallel vectors are relatively easy to define because they are simply scalar multiples of each other. So if vectors are parallel, that implies that they are scalar multiples of one another. And to recall a scalar multiple, if we have a vector A, a scalar multiple of the vector A is a scalar multiplied by that vector A. And what k does is it changes the magnitude. And in some cases, it can also change direction. If it is negative, then it changes direction, and more specifically, opposite. Okay, so it will still be parallel, just in the opposite direction. And that's something we refer to as anti-parallel sometimes. Perpendicular vectors are a bit more difficult to define, and we rely on the dot product to define them. In the previous video, we defined the dot product of a vector A dotted with a vector B. If we have A being equal to A1, A2, and B being equal to B1, B2, we define the dot product as A1, B1 plus A2, B2. However, it can also be defined as the magnitude of A times the magnitude of B times cosine of the angle between them. And here, the angle between the vectors, if I have my A and I have my B here, I have A, I have B, then the angle between them is the tail-to-tail angle, or it can also be written as the tip-to-tip angle, like this. It can't be written in this way, where you have A like this and then B like this. That is not the angle theta. Okay? And the reason why tail-to-tail and tip-to-tip works is because of alternate angles. If I look, this should be B, this should be A. If I look at the angles here, I can see that B and B are parallel, A and A are parallel, and so if I merge these together like this, I can see that I form alternate angles, like so. And so if I'm looking at my angle theta refers to the tail-to-tail or tip-to-tip angle. Okay? So that's the alternate definition. The magnitudes of the vectors multiplied by cosine of the angle between them. And importantly, if we look at cosine of theta, we know that cosine of theta is equal to 0 if and only if theta is equal to 90 degrees or 270 degrees or whatever else thereof. Okay, but most importantly, 90 degrees. Okay, so if I have my tail to tail like this, that's 90 degrees there. That would be 270 degrees, but normally, because we're looking at the tail to tail, we're going to use the smallest possible angle. And we won't use something like 90 plus 360 using concepts of periodicity, because in this case, it's not really that important. This is equal to 450 degrees. So we can say that, but if we're looking at these two vectors, from here up to here, that would be 90 degrees. Okay? So I'll represent that like this. And so if cos theta is equal to 0, any numbers multiplied by 0 will be equal to 0. And therefore, if I am looking at a perpendicular vector, then if A and B are perpendicular, let's say I have A here, I have B here. If A and B are perpendicular, that means the scalar product or dot product must be equal to 0. So A dot B equals 0 implies that A is perpendicular to B. And so that is the definition of perpendicular vectors. And this is particularly helpful in cases like closest approach. So let's say you have a point P here. You have a boat that is traveling from this point here, and it's going along, traveling along like this, like that. And you want to see the closest it arrives to P. The closest it will arrive to P is intuitively where the direction it's heading is perpendicular, at this point here specifically. And so if I want to find my closest point, closest approach, I can define this as my vector position at the time 0. So this point here is where I haven't moved at all. This is where I start. And then I start moving with a velocity vector in this direction. Okay? So this is my point at the point R after a certain amount of time. Okay, and so if I'm considering this vector from RT up to P, I can define this as RP, okay, then this is equal to RP minus RT, okay, so that would be this vector here. And the reason why that is because minus RT is going back to the origin, and then up to RP is that. Okay? And so that is the vector there. I can also define that as my RP, P, relative to my thing here. Let's say this is a boat. So I have a boat. This is equal to my P relative to my boat. Okay? The point P relative to my boat. And my boat also has a velocity vector B. So this means for closest approach occurs when the relative vector of that point relative to my boat dotted with the velocity vector of my boat is equal to 0. And that can also apply to planes. It can apply to a runner trying to run past a point, and so on and so forth. But this is the key application of the scalar product in sort of real-world applications of vectors. And there should be some worked examples in any testing questions, any exam questions. If you need this explained further, make sure you leave a comment in the comment section, and I will go over this in a supplementary video. Now, the next thing I'm going to go over is projection of vectors. When it comes to projection of vectors, what a projection of vectors refers to is if I have a vector A like this, I have a vector B like this, alright, then my projection of A onto B is the component of A in the direction of B. So I can write A in terms of I and J components, but I can also write A in terms of parallel to B and perpendicular to B. So if I consider the projection, I can consider this as a flashlight kind of shining down perpendicular to B, and it will be the shadow of A cast onto B. Okay, so in this case, my shadow would be this vector here. Okay, Now, when we're dealing with projections, okay, we can deal with either scalar projections or we can deal with vector projections. The scalar projection of vector A onto B is the magnitude of this vector, whereas the vector projection is the magnitude and also that direction in B. If I have, for example, A in this direction and I have B in this direction, then my projection is actually going to be in this direction. This is the component of my vector A in the direction of vector B. In this case, really, it's the opposite direction to vector B. But the concept still kind of holds here. So, if I want to find this point here, and I want to find the magnitude of this point, okay? In that case, I deal with the magnitude A, okay? And I have an angle between A and B defined as theta, all right? Now, I know that cos theta is equal to the adjacent side, which is x, over the hypotenuse, which is the magnitude of A. And I am trying to find the scalar x, so x is equal to the magnitude of A cos theta. All right? So let's rewrite that. The magnitude of A cos theta. So the projection of A onto B, the scalar projection that is going to be A cos theta. Alright, so this is the scalar projection. Scalar projection. And the alternative is the vector projection. That's the other thing we need to know. So when we're dealing with the vector projection, we not only have magnitude, but we have a direction assigned to it. And the direction will be in the direction of B. However, we can't just have A cos theta multiplied to my vector B, because that won't be the magnitude. The magnitude of B will actually influence the magnitude of that vector, right? So what we actually need to do to get a vector in the direction of B with this magnitude, we need to find a vector in the direction of B that has a magnitude of 1. Because if it has a magnitude of 1, and we multiply that by a scalar multiple of this value, then I will get a vector in the direction of B with this magnitude, and that's what I want. Okay? Now, in order to get a vector B that has a magnitude of 1, what I'm going to need to do is I'm going to need to divide my vector B by the magnitude of B. Okay, and if I divide by the magnitude of my vector B, then I get a vector in the direction of B with a magnitude of 1. And I can represent that as B with a little hat on it. This is referred to as a unit vector. Okay, and we've already dealt with unit vectors I and J, because I is a vector in the horizontal direction and J is a vector in the vertical direction. And if I consider the magnitudes of these, they're both 1. So I and J are two examples of unit vectors. Okay? If I want to find any unit vector, all I need to do is find the magnitude of my vector and divide my vector by that magnitude. So, to find the scalar projection, and I'm going to represent that with P and a tilde underneath, that's going to be equal to A cos theta multiplied by my unit vector B hat, I'll call it. Okay? And so this is referred to as my vector projection. Okay. There are also several functions on the class pad that allow you to do this sort of thing. And if you would like me to go over something like that in a video, leave a comment and I'll consider that too in supplementary content. Alright, so we've examined properties of parallel and perpendicular vectors. We've also defined and used sort of projections of vectors. There'll be some other applications where you need to find projections of vectors, and those will be in test questions. So the next point is solving problems involving displacement, force and velocity. And to do that, I'm going to introduce a couple of test questions that I've taken from some past tests and exams. Alright, so This first one, I am looking at a problem involving force. I'm looking at three forces applied to a body, one with a magnitude of 300 newtons acting due south, another with a magnitude of 250 newtons acting on a bearing of 50 degrees, and a third that I don't have information about. But I know that all three forces are in equilibrium. That is, the horizontal and the vertical directions cancel out. So I know that one of them has a magnitude 300 newtons and it's acting south, okay? So it is acting in a southerly direction here, and it has a magnitude of 300 newtons, okay? And this drawing the diagrams bit is the most important thing when it comes to any vectors application question. This is probably the most difficult part of any vectors application question. And once you get that done, it's relatively easy to do. Now this next one has a magnitude of 250 newtons, and it acts on a bearing of 250 newtons, and it acts on a bearing of 50 degrees. So that's approximately like this. That has 250 newtons. This is a bearing of 50 degrees, and so I know my other vector will need to be acting something like this, and it'll have some sort of bearing associated with it. I want to find the magnitude. I also want to find the direction of the third force, and that's all good there. All right, cool. So this will have x newtons, and this will have an associated angle with it, which I'll label theta in this case. All right. So I want to consider my vertical forces resolution. Okay. So first of all, I know that in the vertical direction, I have my 300 newtons acting down. My sum of my forces in my vertical direction is going to be equal to 0. All right. And more specifically here, I have 250 newtons acting in this direction at a bearing of 50 degrees. So if I want to find the component of that vector acting in the vertical direction, that will be equal to this side here. And this side here is equal to 250 cos 50 degrees, because it is the adjacent side to the angle 50 degrees. Additionally, I will have a angle here, a force here that's also acting in the vertical direction, and that one will have x cos theta degrees magnitude. Okay, so my first equation will be 0 is equal to 250 cos 50 degrees plus x cos theta degrees minus 300. Okay, in terms of my horizontal resolution, okay, my 300 newtons is only acting in the vertical direction, so I won't consider this. I can consider to the right as positive, upwards as positive, and so if I have 0, my second equation 0, that's going to be equal to 250 sine theta minus x sine theta. Sine 50 degrees here, minus x sine theta degrees. And if I plug these two equations into ClassPad, I will get my solutions. X is equal to this, theta is equal to this. And so from my ClassPad, I get x equals 236.82 newtons, and theta is equal to 53.97 degrees. But if I want to find that as a bearing, that will be in a clockwise direction from true north. And so my bearing, in this case, will be equal to 360 minus whatever that value is. And that is 306.03 degrees. So finally, I have 236.82 newtons on a bearing of 306.03 degrees true. Okay? So that is my final solution in this case. All right. Now, my next application is a sort of, it sort of forms a triangle. This is using your triangle and your parallelogram rule, and it involves vector addition and vector subtraction. Okay. So in this case, I've got a boat trying to cross a river from a point A to a point B. Okay. And OA is my point, this point, and my point OB is this point here. Furthermore, I have a current flowing in this direction. Okay. it is trying to ask us to determine the velocity vector the small boat should set to travel directly from A to B. Alright, so if I have a point A here, that's at the point 60, 35, and I have my point B, I'm trying to get to my point B, which is, in this case, 356, negative 125. And so this isn't actually in the right direction, but regardless, it should be okay. Maybe I will change it up a bit so it's right. So I've got A 60, 35, and I'm moving in this direction to a point B, which has 356, negative 125. And I know that there's a uniform current flowing negative 1.5 plus 2.5 J. And so if let's move this around a bit. So B over here, and that's a vector of 356, negative 125. I have a vector, uniform current moving in this direction. And if I think about my boat moving over the course of time, then the distance traveled by a current that's pushing me will be equal to negative 1.5, 2.5 times the time it takes me to get from the point A to the point B. And now if I also consider, furthermore, my vector A, B in this direction, then the direction traveled by solely my boat, not considering the current, will be equal to A, B times the time taken. Alright? Now, if I consider my vector AB, that's going to be equal to OB minus OA, which is equal to, OB in this case is 356, negative 125, and OA is 60, 35. So that would be equal to 296, negative 160. Okay? So that's my vector here. So from A to B, that's 296, negative 160. Now, if I consider my vectors AB, T, and negative 1.5, 2.5 T, then I know that I will be able to, then I know that A, B multiplied by T plus negative 1.5, 2.5 multiplied by T will be equal to 296, negative 160, which is my A to B. And if I look here, I can see that that is a triangle, right? I have it going in this direction and then in this direction to form my resultant AB, which is this one here. Alright? And so from this, I get two equations. I get AT, take 1.5T, is equal to 296. Second of all, I get BT plus 2.5T is equal to negative 160. But the thing is here, I have three unknowns and only two equations. So there must be some more information in my passage. Namely, here the boat can only maintain a steady speed of 4 meters per second. That implies that my magnitude of A, B must be equal to 4. Okay? And the way I can write that is A squared plus B squared is equal to 16. Okay, so 4 squared that is. And if I plug this into my class pad, I should be able to get my solution. So, regarding my solution, I will be having two solution sets. And importantly, one of the solution sets has a negative value for time. That is, if you're following along with your class pad, you should see that you get a value of t equals negative 54.1 seconds in this case. And obviously we can't consider that solution. The reason why that is the case and why that can happen is that in some cases, if you look at the opposite direction vectors, you could form a triangle that kind of looks something like going in this direction, and then my vector kind of goes weirdly like that in that direction, opposite direction like this, and then you form like that kind of vector in that way. But that's obviously not the solution that we're going for. We're going for a solution where my time is positive. Okay? And so the solution set where my time is positive is where A is equal to 2.56. My B is equal to negative 3.07. And I'm doing this to 2 decimal places just because. And my time taken is going to be equal to 279.14 seconds. Okay, and so my question asked me to determine the vector in the form of AI plus bj. So I have my a value here, I have my b value here, so my velocity vector of my boat is going to be equal to 2.56i take 3.07j. And so this is my final solution. So in this video, we looked at properties of parallel and perpendicular vectors, we looked at projections of vectors, and we solved some problems involving displacement, force, and velocity. The next video, we're going to go over vector proofs, which will take us to the end of the vectors topic. This is probably the most conceptually difficult topic in the Year 11 spec course, and also when you can expand to 3 dimensions, it's probably the most conceptually difficult unit in the Year 12 spec course. But I hope it was relatively understandable, and the key is practicing a lot, so make sure you're doing that in the exercises that I've linked in the description below. Thanks for watching this one, and I'll see you in the next one. Bye-bye.